with the properties of the spin, the Dirac field, the spin 1/2 massive fermion. And we're going to finish by, we're going to finish with two things. One is we could just give the derivation of the analogous of the 2-point function for the fermions. We saw the one for the scalars, you remember? And now we're going to derive the one for the two fermions. And then I will discuss a topic that I only briefly mentioned for the scalar case, which is the discrete symmetries, Poincare discrete symmetry, parity, time reversal for the spin 1/2 field, for the fermion field, because there the discussion is more rich, and you can easily derive the same properties we derive now for the fermion for the scalar field, which is much easier. Okay? So let me see. So for the scalar, if you remember, we derive all basically 2-point functions, just relating them to the time order product of phi and phi Draghian for complete scalar field, of phi for real scalar field. And we can do the same for the fermions. So I start with the time ordered 2-point function, which is t of, let's say, psi of x, psi bar of y. Here I'm adding gamma naught and vacuum. So this is the product of these two fields computed on the vacuum. Remember that this is, each of these spinor bring a spinorial index. I'm not contracting it. So this object is a matrix in spinorial space. And there is a time ordering. The time ordering for fermions is defined similar to scalar, except there is a minus when it's changed to fermions, because they anti-commute. So by definition, this object is theta of x naught minus y naught times the product of psi of x, psi bar of y, minus theta of y naught minus x naught, psi bar of y, psi of x. So when y naught is in the future of x naught, not only you exchange the positions, but you also add the minus sign. Okay? And similarly, if you have a more fermionic field, you compute the time order product, you just order the operators in such a way that they are ordered in time, times a minus factor, minus one factor for each permutation of fermionic fields you have to do to go to that particular ordering. Okay? Similarly for the normal ordering.
Okay? All prime vector is fixed or fixed?
Again?
For all prime vector fixed.
For?
Fixed. They are fixed. All prime vector.
Alpha beta are fixed. So
matrix and one.
right, alpha, beta, beta, alpha. So for each component.
Yeah. These are all prime vector. One of them matrix and another is scalar.
It's similar if you have like more scalar field, phi I and phi j, then you can do the same. Okay, so now we should compute this. In principle, you can just perform a computation like we did for the scalar field, just replace sin psi bar with the solution of the Dirac equation. You have C and the dagger. You replace everything, you find some expression. I'm going to give you an alternative derivation, which is less computation. Let me call this 2-point function as f, which is f is for Feynman. Remember this time order property is also. And this SF is a matrix in spinorial space. There is an alpha beta, okay? So we want to compute this SF. Now let's compute first I the slash minus n applied to SF of x minus y. And this derivative is done with respect to x. Okay? Let's see what happens. So if I perform this product, if I apply the I the slash minus m to s, you see the derivative acts on x. You have two terms when the derivative acts on the field, but you also have a piece when the derivative acts on this theta here. So when the derivative acts on the field, you get I the slash minus m times psi, but psi is a solution of the Dirac equation, so you get 0. So the terms that come from applying this operator to psi are vanishing. So you're only left with a piece where the derivative acts on this theta function. So this is a step function. If you take a derivative with respect to x, you get a delta function. And here you get a minus a delta function, but with a minus you get a plus. So you get and you get a delta function only when you take the derivative with respect to time, because this is the only value on x naught. So out of all these terms, you have only the term which is gamma naught, d naught, dx naught. So you get a gamma naught. And here you get the delta of x naught minus y naught. This stays the same. Psi of x, psi bar of y. And for the second factor, as we said, there is a minus delta from here, there is a minus here, so it's a plus delta. And here is the same with exchange of orders. So you get another delta plus the guy with the opposite ordering, so it's just the anti-commutator.
What way we get the minus sign from delta?
Because if you do the derivative of this, you get a delta. If you do the derivative of this, you get a minus delta. The derivative is if this increase, this decrease, this negative. Okay? So delta is an even function, but the step is an odd function. So if you do the derivative of minus x naught, you get the minus. Okay, so, but you see, this is the anti-commutator at equal time because it's multiplied by the delta. And the anti-commutator at equal time, we know what it is. Well, we know the anti-commutator of psi with the conjugate momentum, which is I psi dagger. Well, one I can borrow from here. And this is just psi dagger gamma naught. And this is I delta 3 of x minus y. So you have a delta 3 of x minus y, a delta of x naught minus y naught, and then you have a gamma naught square, which is 1. So you are left with I delta 4. Okay? Questions? Okay, so now let me take SF of x minus y of the form I the slash plus m of some function which, without luck, well, let me call it a of x minus y, okay? Okay, I just if you want, this is my definition of A. I take SF, I define it as like this. A is the function that multiplied by I slash minus n, return S. And I take this expression and plug inside here. Now you see that I slash minus n times I slash plus n give you minus box plus m squared applied to A equal I delta 4 of x minus y. Right? For the minus, we can make it, put it here. And now you recognize this equation. This equation is the usual equation defining the green function, right? So this A is nothing else than our Feynman green function, the solution of the scalar field, 2-point function. So we're done, because the propagator for the fermion, the 2-point function, is just I the slash plus n times the propagator of the scalar, which we already computed. So all we have to do is just multiply I the slash plus n. So we get SF is nothing else that I the slash plus n of, this was the integral in d for p over 2 pi to the 4, I over p squared minus n squared plus I epsilon, if you want, e to the minus I p x minus y. So this was the, remember, the Feynman propagator. And now we have to apply I the slash plus n. So the derivative only acts on x, which appears here. It brings down a minus ip times I. It gives you a p mu gamma mu. So this is also equal to the integral in d for p over 2 pi to the 4. There is a I, and then there is a p slash plus m over p squared minus m squared plus I epsilon to the minus I p x minus y. So you see, this is a matrix. P slash is a matrix in spinor index, so this has a field. So if you use the relation p slash plus n times p slash minus n equal to p squared minus m squared, right? Because p slash is equal to p squared. And you replace this p squared minus m squared with the product of these two. You can simplify 1 p slash plus m with the numerator, and so you can rewrite this object here also as I over p slash minus n plus I epsilon equal minus I p x minus y.
So this is matrix.
Sorry?
This is a matrix? So
yeah, this is a matrix, so be careful. This is the inverse matrix of p slash minus n.
Okay.
And inverse matrix always like this. Inverse matrix.
Huh?
Inverse matrix is always existing. Like all the division.
It does not exist when p squared is equal to m squared, which is the pole of this guy. On the other hand,
So
the
poles are
whole
also
integrand that does not exist.
So
So
poles are non-invertible matrices.
the poles are avoided by I epsilon, right?
Which is also a matrix.
No, well, it's the identity matrix. Also, M is the identity matrix. If you want, this expression is never used explicitly. It's only a shorthand notation for this. When you do computation at the end from here, you always go back here. So you have all the matrices in the numerator, easy to apply. But this is short. It's a shorthand notation. As you see, it's nothing else than the inverse of the Dirac operator. The Dirac operator in momentum space was p slash minus m applied to the spin equal to 0. And this is the inverse. Because this object vanish when you go on shell, when you satisfy the dispersion relation for your particle, p slash is equal to m. And this was exactly the analog of what happens to the scalar field. When p squared is equal to m squared, you get the divergence here. And this divergence was associated to the fact that this was already encoded in the free equation. This is just a response to a source.
Why we ignore I epsilon in the...
We ignore.
Because we...
Oh, here. We remember that I epsilon is always a limit when I epsilon goes to 0. So first order is negligible. If you want, you can remove I epsilon, define everything in terms of contours that avoid the poles, and then at the end you restore I epsilon. But at the end, this notation is, you can just see as a reminder of this. And here is the usual description. Like for the complex scalar field, you can associate some pseudo interpretation of this two-point function as creating a particle at one point and annihilating on the other point, when x naught is in the future and y naught is in the past. Then you first, from the vacuum, you first create a particle using the C dagger inside here, and you annihilate it using the C here. When y naught is in the future of x naught, then you first create an antiparticle, because now you use D dagger from side on the vacuum, and you annihilate it in y. And as for the complex scalar field, we use inverted arrow because we follow the charge. So since the antiparticle has opposite charge, if you want, if the antiparticle is going this direction, the current is going the opposite direction. So that basically this object is always represented with the arrow that starts from y and ends up on x. So start from side bar and up from side. If you follow the flow of the charge. This is just notation. Oh, and there is an extra minus when you change the orders. And exactly like for the scalar field, you can derive everything from the Feynman propagator, taking the imaginary part, blah, blah, or you can just apply this guy, I slash plus m, to the corresponding two-point function, green function. For example, if you just want to compute 0 psi of x, psi bar of y on 0 without time ordering, for the scalar case, this was what we call delta plus of x minus y. And now it's just I the slash plus m of the same guy. If you compute the inverse, there is an extra minus because it's change the family. And if you, since we already computed the explicit space dependent of the two-point function, for example, in this case, you can compute directly also in this case the x dependence of the two-point function. So you remember gf of x minus y was some prefactor times the Bessel function of x minus y square root of x minus y squared. You just apply I the slash, which is the derivative plus m of that Bessel function. You find another Bessel function with multiplied by gamma matrix. So you find a matrix of Bessel function, which is the propagator in a position space.
And then we say that, for example, when the mass goes to 0, then it goes the Bessel function as 1 over the distance. It's the same thing in this case?
Well, it's the derivative of that. Right? It's I the slash. This function is exactly the same as before.
Yes.
So when m goes to 0, it's still true that this is like 1 over x squared, and you're just taking a derivative of that, so you will find some x slash over x. And when a large, instead in the opposite limits, when the product of m times the distance is large, that Bessel function was going exponentially to 0. Also in this case, you just take a derivative when exponential to 0. I think it's proportional to some exponential separation. Okay, so this is all. For the free theory, also for higher point function, the discussion follows the one for the scalars. The odd ones at 0 because of symmetries. The even one are can always be written as a product over two-point function. Which is this one. Okay. More questions? So clear? Anyone? Okay. So just take note of this, put it apart, we'll use it later. Okay, so last topic, discrete symmetries. As we will see, there are three relevant discrete symmetries we're going to consider, mostly for the fermionic Dirac field. We'll start with the first. It's parity. Okay, so the parity transformation is part of the Poincare symmetry, which is a discrete part, it's not part of the proper group. And what it does is just invert the spatial directions, the three spatial directions. So on vectors, what happens is that V naught is unchanged while the spatial part is inverted. So there will be transformation. V mu goes to lambda mu mu parity. V nu is represented by a 4x4 matrix, which is 1 minus 1 minus 1 minus 1, proportional to G mu nu, right? Okay, so this means that for our fields, we say that usually under a Lorentz transformation, a field psi of x transforms into something, which in general is the form of some matrix S applying to the spinorial index, the spin index, times psi on x prime. X prime is lambda minus 1 transformation. So this is x prime is basically the analogous x naught minus x vectorial, just write it as x prime. And what about S? The representation of the parity transformation for spinorials, spinor field. This S is basically represented by the matrix gamma naught. In fact, if you take gamma naught, gamma mu, gamma naught, which is, or if you want, you remember that you want that S minus 1 gamma mu S is something that is lambda mu nu gamma nu. And lambda mu nu gamma nu is nothing else, well, I write it. It's lambda mu of parity gamma nu. This is gamma, for the zero component, it's the gamma naught. For all the spatial component, you have just a flip of sign. So you want something that does not touch the zero component and flip the sign of the spatial component, and gamma naught to make the job, because when mu is equal to naught, you have gamma naught cube, which is gamma naught. When gamma mu is I, since the anti-commute with gamma naught, you get minus gamma I. So gamma naught, if you want, is the explicit representation of the the representation of the parity operation for spin. Okay, so let's see that this is a symmetry of our Dirac-Lagrangian. So we start with psi bar I slash minus m psi of x. And we transform the fields. So this transforms into psi dagger of x prime, gamma naught, s minus 1 is gamma naught, but gamma naught times the gamma naught inside the psi bar, get 1. Here you have, or maybe let me keep it explicitly, gamma naught. Then I have I d mu gamma mu minus m times psi times gamma naught psi of x prime. Okay? Just replace psi with this transformation here. Now you see that gamma naught on m does nothing, gamma naught square. Gamma naught, gamma naught is just change gamma mu into gamma mu lambda p mu gamma nu. But the derivative with respect to mu, this is the derivative with respect to x. When you apply to psi of x prime, also produce an extra minus for the spatial components, which simplify with the minus of the spatial component that you get from the computation of gamma naught with gamma I, so you get an invariant. So you get the original Lagrangian. Okay? We found that Dirac-Lagrangian is invariant under parity. And now let's see how parity acts on the states. So you remember we can define at the level of operators, we can define the identity, following identity that the unitary transformation implementing parity on the Hilbert space, UP, applied in this way to a field of psi of x, must return basically S times psi of x prime. But this is SP, which is just gamma naught. This is at the level of operators now. Okay? This is the analogous identity that we did for Poincaré transformation to argue how the creation annihilation operator was transforming under the transformation of the Poincaré group. Now we do exactly the same exercise for the discrete symmetries. Okay, so now we just replace this object here. This is trivial, it's just the usual expression for the solution of psi in terms of C and the dagger, with just the dagger U on one side and the other. This dagger U only acts on the hyperspace, so basically you can bring them just inside, just around the C and the D operators. On the other side we have this guy, so this must also be equal to, let me write it explicitly, here we have an integral in D3P over 2 pi cube, 1 over 2 omega p, sum over helicities, C tilde PH, UPH e to minus IPX prime, plus, I'll write a gamma naught here, plus D tilde dagger PH, gamma naught DPH e to the IP x prime. So just brought gamma naught inside and replace x with x prime. Now I can make a change of the variable of integration p in minus p. This is only the spatial part of p. As usual, this is invariant. P becomes minus p because this is just a spatial guy. And now this becomes p prime for x prime is equal to p times x. And I forgot also the helicity flips. Because you remember, if you change p, the helicity is defined as sigma dot p. So if you change p, you also have to change the helicity flips. Now, there's a following identity that gamma naught of U P H is equal to U minus P minus H, and gamma naught of V P H is equal to minus V minus P minus H. To see this, you remember the definition of this spin of UPH is the spin which is eigenvector of the Hamiltonian with eigenvalue omega p, and eigenvector of the helicity with an eigenvalue h. So now if you take this combination, gamma naught times u, we apply the Hamiltonian. The Hamiltonian, remember, was gamma 0 gamma I p plus m gamma 0. The m gamma 0 part, commute, gamma 0. But the special part, which is gamma 0 gamma I, anti-commute. So if this is the eigenvalue with momentum p, this combination is the eigenvalue with momentum minus p, or the Hamiltonian with the minus p. And analogously for the helicity. And analogously for v, and there is an extra minus minus coming from the fact that the eigenvalues of gamma naught is plus or minus. As an exercise, you can just replace the explicit expression of the u's we saw it. You apply gamma naught, you will see that you find the u with minus p minus h. So using these identities, we can relate gamma naught of u minus p minus h with uph, and v minus p minus h with minus gamma naught uph. So this guy here is UPH, and this guy here is minus VPH. So this guy, which was this term, must be equal to this. This is exactly the same expression, except that here we get U dagger C U, and here you get U dagger D U. So by just matching term by term in these two expressions, you get, for example, for the here, you get that C of minus P minus H tilde must be equal to U dagger CPH U. And analogously, D tilde minus P minus H is equal to U dagger dPH with a minus. Sorry, these P's are the parity and the other P are the moment. Okay. So you see, when you perform a parity transformation to a state, the state is a collection of creation operators and particles. When you apply this parity transformation with this unitary transformation UP, you just convert the creation relation operator of particle momentum P and H with the same creation relation operator, but with momentum minus P and minus H. So every particle, for each particle, its momentum gets inverted, the momentum, and each helicity gets inverted. Notice the helicity is just the product of spin times momentum, which means that the spin is not inverted, as it should, because it's a pseudo vector. Instead, the momentum is inverted. As expected from a parity transformation.
Pseudovectors also exist outside of the spinor context or gamma matrix structure, right? Like R cross B is also transformed as a pseudovector
Yes.
under this parity
Under
transformation.
parity.
You didn't need to refer to a gamma matrix structure.
Yeah, yeah. Well, yeah. At the end, parity is just acting on the space component, right? So then you can just use the SO3 rotations, and everything that was valid for 3 vectors of SO3 will be biased validity here. So this is really the implementation of the usual parity in this theory. It's, nothing, it's not this parity changes. The parity transformation changes in this context.
For example, if you have a pseudo-vector as a list of numbers, as a tensor, for example, as a component of a tensor, in this particular case, we would recognize pseudo-vectors if they involve gamma 5 or not. That would give us a clue that if this transform is a pseudo-vector or vector under parity, right?
We will see. In principle, now I can compute how any bilinear transform under parity. We saw that the Lagrangian is invariant. Next, you can compute psi bar gamma phi psi, for example. And then you'll see that since this transforms with the gamma naught, then gamma naught anti-unit with gamma phi, this changes sign. So this is not a scalar, it's a pseudo-scalar. And analogously, this guy here, you have a gamma naught here. When you pass a gamma mu, you change like a vector, because the spatial components will flip sign. But then because of gamma 5, you get the opposite. So only the time component switch sign, and the space component not. And this is indeed transformed as a pseudo vector. But everything just follows from our way to define the way spinors transform, and then you find all the.
In the case of momentum and spin, let's take a special case where they both in z direction. When we do the parity transformation, they will be in the opposite direction, so the density will be 0 at that one, right?
No, it's a product, so it's not 0.
But it's the projection.
So you start with the momentum in this direction and the spin in this direction, right?
Right.
And the density is just P versor or P over P dot S, which is SA plus 1. Then if under parity this just flip side, this just flip side is minus.
Mix it with close.
All right? Okay. There are no more questions. I'll go to the second one. Oh, for scalars, maybe just to give an aside. For scalars, you don't have this under transformation under parity. You don't have this S. So you only have a phi of x going to phi of x prime. But in principle, so if you have a real scalar, you are free to introduce also a minus 1 or not, as a freedom to define the parity in this way. So if you sometimes the theory is invariant only if phi x transforms this way. For example, imagine that in my Lagrangian, that one, I also have a scalar field, a real scalar field. Sorry. This theory is invariant under parity, where parity acts on this way on the fermion, and acts either this way on the scalar, or it acts on this way on the scalar. In both cases, the theory is parity invariant. Okay? If you want the difference between this and this, and instead in this case I say I'm doing parity, and in this case I'm doing parity and an extra Z2 symmetry, you remember phi minus phi. transformation. If you want to have I have two symmetry, parity, and this is Z2. Now let me add to this Lagrangian the term phi of x, psi bar, gamma phi, psi. And I need probably to put an I here, because psi bar, gamma phi, psi is anti-emission. So if I now try to do the parity transformation, this bilinear psi bar, gamma phi, psi transform in minus itself. Because you get gamma naught, anti-commute to gamma phi, you get an extra minus. So now, only if I define parity in this way, this term will be invariant. This I cannot. If I define it this way, it's not a symmetry. So the only symmetry, the only parity that you get is the transformation that transforms the fermions in this way and the scalar in this way. So there is still a parity transformation, but it's implemented in this way. When this is the case, this scalar is called pseudoscalar because it's parity odd. You might already encounter the values. For example, pions are of this kind. Pions are some of the hadrons in this strong interaction. If you want to decouple two fermions in this way. Okay. Can I erase? Okay, now we move on to the second discrete symmetry. One we already saw for complex scalar field is charge conjugation. So remember, for scalar field, this was the symmetry exchanging phi of x with phi dagger of x, not touching the space-time coordinates. And at the level of creation relation operator, we're basically exchanging what we call the A and the B, the particle and the antiparticle. So for fermions, we want to realize something similar and have a symmetry that exchange psi with psi dagger. Right. Now, first of all, if you just take dagger, since there is also an index here, if this is a vector, a column, this will become a row. Let's keep it a column, just add also a transpose. So here, if you want, we have like two types of indices. The indices for the operators inside psi, the creation and relation operator. For those, I'm just taking the Hermitian conjugate. Instead, for the spinorial part, I'm just taking, if you want, dagger time t, which is just the star, just taking the complex conjugate. Okay? Similar to this, when for a classical field, you just take phi and phi star, and when it adds on the operators, you take the Hermitian conjugate because you know their matrices. But on top of this, we are also free to add a transformation, let me call it, well, usually it's called C. It's a transformation taxon on the spinorial indices, and it's the analog of what before we called S of lambda, right? but now it's okay. Good. So it's we have the freedom to also add a rotation of the components of the spinors, because now there are more of them. And we will see that we get a symmetry of our Dirac theory if for a particular choice of this C. So we cannot just take it trivial, okay? But there is a particular choice that guarantees the existence of a symmetry, which indeed exchange psi with this complex quantity. So if this matrix C is such that C dagger gamma mu C is equal to minus gamma mu star, and this C is such that C dagger C is equal to 1, so identity, so it's a unitary. Then we will see that the Dirac-Lagrangian is invariant. So if you can find a matrix C that satisfies these two conditions, Lagrangian is invariant under this transformation. Well, can we find a matrix that do this? Yes, it's always possible to find one. And for example, for the representation of the gamma matrix we saw, like Pauli Dirac or Bayer, it's enough to choose C equal to I gamma 2.
For both of them, or
Yeah, I think so.
both
Or maybe one in the sense gamma naught.
or is it important?
Well,
this is very.
No, all is important that there is this matrix that do this. Which matrix is may change.
Gamma 0,
Huh?
gamma 0 multiplied with
We'll see. So let's choose this and see. Substitute here. Well, first of all, I gamma 2 times minus I gamma 2 dagger is 1. Because for our choices, gamma 2 star is equal to minus gamma 2, right? Because gamma 2, if you remember, was the one with the I sigma 2, which with the sigma 2, which were purely imaginary. And gamma 2 is anti-emission. Only gamma 0 was emission, gamma 2 was the gamma I were anti-emission. And okay, and then gamma 2 is also equal to gamma 2 yes, transpose. So now if you now take this equation, you can check that indeed C dagger it's minus I gamma 2 dagger times gamma mu times I gamma 2. Gamma 2 dagger is minus gamma 2. So this is I gamma 2. I square is minus, so this is minus gamma 2 gamma mu gamma 2. So for gamma naught, you get gamma naught anti-commute, so you get gamma naught. Minus gamma naught. For gamma I anti-compute, you get minus gamma I, it's called gamma 1. For gamma 2, you get gamma 2 square, which is minus 1, so you get gamma 2. For gamma 3 anti-compute, you get minus gamma 3. But gamma 0, gamma 1, and gamma 3 were real, so these are also equal to the star of themselves. Gamma 2 instead is purely imaginary, so it is also equal to minus gamma 2 star. So indeed, they satisfy this relation.
Why would we require that relation?
We will see. If we require this, now I'm going to show that if we require this relation, this transformation is invariance of the Lagrange.
That leaves the Lagrange invariant.
First, I'll show that there is one choice that satisfies this, at least one choice that satisfies this relation. And now we'll see that using this relation, the Lagrangian density is invariant. So this is this transformation indeed is a sigma. So let's see. I start with the usual form of the Lagrangian, and I perform transformation. So first of all, if psi goes into C psi dagger transpose, if I take the dagger, psi dagger goes into the dagger of this, which is psi transpose C dagger. The dagger of this is psi transpose C dagger. So this means that the psi dagger inside here goes into psi transpose C dagger. There is a gamma naught I the slash minus m, and psi goes into C psi dagger transpose. Okay. Now I take this C dagger, can put a C dagger inside, and I use this relation here. So this is also equal to psi transpose. The first, convert gamma naught in minus gamma naught star. The second, convert the gamma mu, which are here, into minus gamma mu stars. So I get minus I d slash star minus m. The C now disappears. I'm left with psi dagger transpose. So this minus become plus. Okay. Now let me take, so this in spinor space is just a number, right? So I can take the transpose of this number, it's nothing. So I just take, this must be equal to its transpose. So the transpose of this is psi dagger. The transpose of this, which is just I d slash dagger plus n. And this derivative was acting on this field, which now flipped on this side. So I have to remember that this derivative acts on this field here. Then I get gamma 0 dagger, which is equal to gamma 0, and psi here, and the minus here. Why? The last minus. I took the transpose of this. Took the transpose of this, so I get psi dagger, the transpose of this, transpose of this, transpose of this, and I added the minus. Nobody's a crew? Because in order to do this, I exchanged two fermions. And the anti-commute, okay? Okay? Now the derivative, okay, now gamma 0 I can bring on the other side by just multiplying gamma 0 squared here, right? And gamma 0, gamma mu dagger, gamma 0 convert this in gamma mu. So basically gamma 0 goes on the other side and make this psi bar. This minus I bring in. And now this derivative and this becomes without the dagger, because it's going to gamma 0. And now this derivative I just derive by parts, so up to a total derivative. This is plus the derivative acting on psi. And I get up to a total derivative. So I get the initial again.
At first we put the daggers to denote that we put daggers on the creation and annihilation operators that are hidden inside, and then we take transpose one more dagger on the spinor index, and those two daggers cancel each other at that stage, for example.
Which stage?
Like at the very left of that, under that one. We take the dagger of the left-hand side at the left equation.
Yes.
But
The dagger acts on everything, not only the spinor.
So, yeah. The first dagger in the left-hand equation
Yes,
is referring to the operator dagger,
to everything.
to everything.
Both operators and
the
spinoria.
also.
Yes. And then we undo the transpose part of this dagger
So
in the
new
spinoria.
dagger can cancel that dagger.
Yeah, so on the operators, you get a full dagger. On the spinors, you just get a star, a
Because we
complex
take it back
conjugate.
with the
Because if you
transpose.
take dagger and transpose. So the dagger is always on everything, the transpose is only on the spinoria part.
And if we have a scalar side by side, and we take transpose of it, of the dagger, are we also exchanging fermions when we do that? And we need to put a minus sign.
If you just, yes, if you just take the transpose of two fermions, what you're doing is that, the transpose is just, it's almost stupid. If you write psi, the operation of transpose is stupid, because if you just write psi in components, it doesn't matter how you order them, right? So you just keep track of the saturation indices, and you can write whatever you want. Then, if you invert the order, you have to put a minus sign. It's just that the transpose, if you want to keep the notation without explicit indices, then you need some certain order to read the contraction of indices, and then you are forced to flip the position of the spin. If you take the Hermitian conjugate instead, no. If you take a Hermitian conjugate of psi dagger psi, you get psi dagger psi.
That's complex.
I didn't understand. How do we get rid of that minus sign in front of the D slash?
The last
Yeah,
one?
it was operating on the left, and then
Yes, so if I have a psi dagger d left slash psi, this is equal to psi bar minus psi bar d slash psi plus the derivative of psi bar gamma mu psi. I derive by parts. So get a minus the derivative from the other guy, plus a total derivative. We don't care because the Lagrange total derivative does not contribute to the equation of motion.
When you write it, is it the same as del of psi bar times psi? When you mean
This one.
no, yes.
Yeah, this really means that gamma mu d mu. It's just that in order to keep it contracted with gamma mu, I have to write it here, and then I put the arrow. Because this derivative was acting here, right? So I transpose, it will be acting there. Okay? Okay? Okay, so this is a symmetry, and now we want to see how it acts at the operator level on the creation operators. We're going to need identities similar to the one we wrote before with the gamma naught up to u give v, blah, 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 which is the following. Consider p slash minus n acting now on CVP star. Okay. Let me compute this for a moment to see why. This is also equal to C dagger p slash minus n CVP star. And now I'm going to use the properties of the C matrix to convert that into, you see, C dagger gamma mu C was minus gamma mu star. So this is equal to that. And this I can also write as C of P slash plus M PP all star. This is just the star. There is a minus. Okay. But P slash plus M on VP is 0. So this is 0. Which means that this was 0. But this means that this object here must be a UP. Because C slash minus n times the vector x of 0, 1, that vector is a UP. So we get an identity that C VP star is equal to UP, and you can perform the same exercise. You find that C UP star is equal to VP.
Is it only possible because we can see that it's a transformation solution for UB?
If the definition of UP is the eigenvector with the eigenvalue of P slash minus n. P slash minus n applied to a 4 spinor equal to 0 is what defines a UP. So it means that this guy here, this combination, must be proportional to UP. Okay, and now we do the same exercise we did before. We basically use the relation between the unitary transformation of states implementing charge conjugation with the field psi of x, which must match the transformation property of psi of x, which was C psi dagger transpose. Okay, so this is the usual combination. So just compute this. And this is now integral in B3P over 2 pi cube, 1 over 2 omega p, sum over h. Now we have the C gets a dagger. The U here get a C U P, and there is a dagger and a transpose, so it's a star. The D gets a dagger, but it was already dagger, so it becomes normal. And the V gets only a star. And now you use the fact that C U star is equal to V, and C V star is equal to U. And we match with U psi U. And I made a mistake because there was still a star acting also on the coefficient. Okay. So now you see that the coefficient of U e to the minus IPX inside here is just U dagger C U must match with D. And this coefficient, which is U dagger B dagger U, must match with C. So indeed, the implementation of the unitary transformation of this symmetry on the states exchange creation annihilation operator between particle and antiparticle. So you just convert a state made of some number of particle and antiparticle in the same state, but you exchange particle and antiparticle.
Charge operator also switch sign, right?
Yes. So for example, can compute psi bar. What is the charge operator for the Dirac field? In particular, the current, the conserved current, was psi bar gamma mu psi. So exercise, you to the transformation you get psi with a C die, here you get minus gamma C, and then you get minus. To make it over. Exercise. Okay? Other questions?
In that case, we could also choose not UP but minus UP, right? Because both of them are 0.
Yeah. All this transformation parity, charge, conjugation, you can add a phase on the transformation.
So then this part will also change, right?
There's a phase here. All these formulas are defined up to a phase, but typically the phase at the end is not phase. It doesn't matter. or in this case, the phase you can reabsorb also as part of the U1 transformation. Okay. Other questions for this? Okay. Then I'll move on to the last one, which is also the most tricky one. Which is time reversal. Which is the last part of the Poincaré group. And it's more tricky because, as we will see, cannot be implemented as a unitary transformation to the state. And the reason is as follows. So let's take a state, for example, the Schrödinger picture, which evolves with time. And let's perform a time reversal shift, which we will parameterize as some transformation u applying to the state A of t. And A of t is nothing else in the Schrödinger picture as A of 0 with the evolution operator, which is e to the minus IHT. On the other hand, under time reversal, you like that this state transforms into the state where time is reversed. So A of minus t, which by definition is just e to the I ht times A of 0, which is also equal to e to the I ht q of A in 0, where because u at equal to 0 is self-reversed, it is the same. But then you see that u, if it's a unitary transformation, cannot commute with Hamiltonian. Because this guy must be equal to this guy. If you commute with Hamiltonian, you will pass through, and its action on the state will not be the one of time reversal. So either it's not a symmetry because it doesn't commute with Hamiltonian, or it is a symmetry, as we will see, commutes with Hamiltonian, but when it goes through this guy, it can flip the sign here, because it can also act on C numbers, not just operators. So you can define what is called the anti-linear, anti-unitary operator, which is an operator that not only acts on states, but also take the complex conjugate of the coefficients where it acts on. So basically, if you take this anti-unitary operation and you apply to a generic state, which is a linear combination on some basis, here is basically equal to notice the definition of the anti-unitary operator when you act on a linear combination of states. It returns a linear combination of the transformed states, but with complex conjugate coefficients. So if you define this operation like this, then when this guy passes through, he can commute with H, but when he passes through, it just flips the sign, because it's a complex number here, and you return this. So it will be compatible with what you expect from time reversal and with the commutation with the Hamiltonian. The price you have to pay is that this transformation is not implemented by a normal unitary transformation, but by an anti-unitary transformation defined this way.
Why they should be equal?
Well, this is the way we implement the transformation, and this is what we want this transformation to do. We want this transformation to flip the time. Otherwise, it's not time reversal.
Such a U that makes this transformation.
Yes. Yes, because we want time reversal, otherwise it's something else. Right? So either it's not time reversal, or it doesn't compute with Hamiltonian, or it must be anti-unitary. In fact, it follows from some theorems that while compact symmetries can always be represented by unitary transformation, non-compact ones not necessarily. And indeed, Poincaré is non-compact, and basically the only generator that shows this effect is the time reversal, which must be implemented with anti-unitary transformation. However, notice that this fact does not clash with what we expect, what we want, symmetry transformation to act on states to preserve the physics. Remember that typically we want a symmetry to be implemented by unitary transformation because we want that when we compute probabilities, they are the same. So when we compute an amplitude, which is a scalar product between a bracket, and we transform the system, we get the same result. So imagine you take a product of two states, A and B, and we transform them into B prime and A prime. This object here, of course, if this is a unitary, this is obvious, right? Because this will be B, U dagger U A, and U dagger U is 1. So this is equal to BA. But this is also true if we have an anti-unitary operator, because this maps into basically B, U dagger U, A, star. Takes the complex conjugate. If we want this operation here corresponds to take this, because it inverts C with the C star, and on the basis invert this basis into the basis which is C.
So for example, if we have a finite dimensional Hilbert space, then anti-unitary operators are not just matrix multiplications.
No, they're not a linear operator.
They are not linear.
Yeah, anti-linear operator are called. So the amplitudes will not stay the same. The amplitudes are changed under this transformation into the complex conjugates, but what is physical are always amplitude modulo squared, and those will not change. So implementing a symmetry with the anti-unitary transformation is still allowed. And this is the way this kind of transformation act.
But then eigenvalues is not real or something. No.
No, there will be. Eigenvalue what?
No, it was for Hermitian operators, not unitary. I mean, having anti-unitary operators.
No, these are not observable.
Yeah, yeah.
These are the transformations.
Yeah.
Okay. Okay. Any questions? Now I will proceed in a different path. Instead of showing this is a symmetry, blah blah blah. I will first see how we want the symmetry to be implemented at the level of creation-elation operators, and then we'll see that basically I follow a different path. So under time reversal, we would like that the creation annihilation operator C and this transformation will transform into a U dagger C P H U, which is equal to, well, under time transformation, what do we want? We want that momentum are inverted because we're going back in time, right? So P is minus P. And the helicity, no. Because the helicity is the product of P and the momentum and spin. Momentum flip sign, but the spin also flip sign if you go back in time, because if you have something that rotates on one way, if you go back in time, you rotate the opposite way. So the spin inverse, momentum inverse, helicity do not inverse. So this is what we want at the level of creation and annihilation operators for the time inversion. And analogously for the antiparticle, should transform in the same way. Okay? And now you can compute time. The product U dagger psi U, which must fit, which must match with the transformation on the psi field, which will be implemented by some matrix acting on the spinors, like the C matrix, the S, and computed in the time inverted argument. Okay. So let's compute first this piece here. So this must be equal to some matrix, let me call it T, on the spinor index times psi of x prime. X prime now is the 4 vector for the position where only the 0 component is inverted and the time component and the space component are not, because it is really time inversion. Okay. And this T is some matrix acting on the spinor indices, like the sigma, the gamma naught, blah blah blah, which still has to be specified. We want to find a suitable matrix here which preserves the symmetry of the Lagrangian and implements this type of transformation. Okay. So I can write the identity also writing this and this, just change variable. Now let me compute the left-hand side. So the left-hand side will be integral in d3p over 2 pi cube 1 over 2 omega p, sum over h. Okay, then we have a C, but with the U, C, U dagger C, U, which must match with the C minus pH. So I can write directly C tilde minus pH. Then I have UPH. Star, because U is anti-unitary, so when it passes through a number, you just take the complex conjugate. And here I get e to the I px, because again I change the complex conjugate, and this x is an x prime, because I'm computing on x prime. And then I have analogously here a d dagger minus ph, a d ph star, e to the minus I px prime. Okay. Okay, so now this product here, now I can do the usual change of variables of integration, p minus p. So this is invariant as usual. This becomes a plus p. This becomes a minus p. And this becomes a minus p, only the special part. X prime is inverted, only the time part. So together, we just put an overall minus. Similarly, here I get a plus p, here I get a minus p, and here I get an overall plus. Now we should match this expression with the expression where t act on psi and find the good t, the good job. Okay. Let me declare which one is the good t and see if indeed it is. Let me take this t to be gamma 1, gamma 3. You see, already use gamma 0 for parity, gamma 2 for charge aggregation, so we use gamma 1, gamma 3 for the rest. Notice that T dagger is gamma 3, gamma 1. T dagger is 1. And T dagger gamma naught is equal to gamma naught T dagger. T dagger gamma 2 is equal to gamma 2 T dagger. T dagger gamma 1 is equal to 1 gamma 1 T dagger. T dagger gamma 3 is equal to minus gamma 3 T dagger. That is, of course, it commutes with gamma 0, gamma 2, because it only involves gamma 1, gamma 3, and anti-commutes with gamma 1 and gamma 3, because they're already there, one of them and the other. This is just a property of this product. What you're going to do? Okay, let's take our favorite equation, defining the pH. Let's write it explicitly in components. So we get omega p times gamma naught minus p gamma vector minus m UPH equal to 0. you see that here what we need is u star or minus p. So let's take the star of this equation. Gamma naught is real. And let's take the minus p here. Okay? So u minus p star satisfy that equation. So now let's multiply by t dagger everything. And now let's bring T dagger through the gamma matrices using these relations. So T dagger gamma naught pass through without doing anything. And then when it passes the gamma I, it basically invert 1 and 3 and keep gamma 2. So this is basically, but gamma 2 is the only one that flips sign because of the star. So at the end you get minus p gamma minus m t dagger u p h star equal to 0. And this was our initial equation p slash minus m, which means, sorry, this is minus p, which means that this combination is nothing less than UPH. Because the solution to this equation is p slash minus m. So we found that T is the right one, right? Because now on one side of this equation you have u minus p h star. On the other side you have t times uph. So if this is equal to this, it means that t uph is equal to u minus p h star. And of course you can repeat the same exercise with a b. So we found the transformation that implements the time reversal at the level of the spinor field. And now the only thing we left to check is that this is a symmetry of our Lagrange. Here I'm doing one thing slightly different than usual, but I can do also similar, but it doesn't matter. Let me work at the level of theoretical level of operators for the Lagrange. So let me check that basically U Lagrangian as an operator, U transforms as a scalar under. Okay, so I want to prove that this is equal to L of x prime, where x prime is only t inverted. If this is the case, the action will be invalid at the level of operators. So if you write it explicitly, this will be ut dagger psi bar of x I d slash minus m psi of x ut. Okay. I add the u dagger and the u dagger here. And I'm going to use this identity here. So we left this term here will become a psi bar of x prime times the T dagger. Then I have u dagger u of this. This is not an operator, but it's still complex, so I have to take the complex conjugate because it's anti-unitary. So I get a minus I d slash star minus m, and then I have u dagger psi u, which is t psi of x prime. Now I have to use these identities. So you see that T dagger, gamma naught T and gamma 2 do nothing, gamma 1 flip sign, and gamma 3. So here you get a flipping for gamma 1, gamma 3, gamma 2 because it's a star, but not gamma naught. So this is equal to psi bar of x prime. So for gamma naught there is no flipping, so it remains minus I d 0 gamma 0. But all the other flip signs, so it becomes plus I d I gamma I minus m psi of x prime. But finally, this derivative with respect to time, this is a derivative with respect to time. Here I change the sign of time. So this is a derivative of this argument with a minus in front. So I get that this is psi bar of I d slash minus m psi computed at x prime, which is my Lagrangian computed at x prime. So the Lagrangian indeed transforms as a scalar operator under time inversion. And the action is invalid.
Why did you take the conjugation from second line to third, or derivative and R?
From here to here, I took a star here because I have a u dagger u, so it's anti-unitary. So if it takes the complex conjugate of the numbers which are in between.
And we pass.
Yeah, when we pass this u to marry this u dagger, we pass through there and it takes star of everything. You remember that u of c something is equal to c star u something.
We could pass through gamma matrices, these U's, right?
Gamma matrices. Yes, but gamma matrices are just numbers. This u acts on the Hilbert space.
At that operator level.
At the operator level. This u at the operator level, this t is at the spinorial.
So actually we have three levels: spin matrices, gamma matrices level, Hilbert space level, and the Lorentz vector level.
Well, gamma matrix and Lorentz vector is same.
Yes, that's same record. Okay.
Yeah. One is the one you have also at the classical field level, and then when you go to quantum, you get a new space which is the Hilbert space, and that is a separate space. Yes. So the u always act on the Hilbert space. All the rest are just numbers. While this t acts on the spinorial index, so they only act on the spinorial space and not on the Hilbert space.
Could we apply all three symmetries at the same time?
Yes. But before, any question here?
Or could we do the same test for the other two symmetries too, like at the operator level?
Yes. Yes. Nothing will change. Here I'm forced to use the operator level because I need the anti-unitary property of this transformation. I could have avoided that, but then I should require, so I could do everything at the classical level in principle, but also the classical level I should require that this T is anti-unitary. And then when it passes through here, it do the same job. It's up to you.
Which is an anti-unitary operator at the Lorentz representation.
Yes.
Space.
Yeah, because you cannot represent the transformation, you simply cannot represent the transformation with the unitary.
So if we had that situation, we need to put some finite dimensional matrix that acts on the spinor vectors, right? If we explicitly try to write T.
Oh yeah, it's not a linear operator, so you cannot represent with the matrix. It's just some operator that flips, it takes the complex conjugate of the C numbers it encounters. Yeah, it's a little bit. Don't know what else. More questions? Okay. So now I summarize all the symmetries. So you have all the results together. So let me make a list of all possible fermion bilinears. So you get psi bar psi. You can have I psi bar gamma phi psi. I put the I because I want the emission operator. You have a vector. You can have the gamma phi gamma mu vector, and you can have the tensor, the commutator, right? Gamma mu gamma nu psi. Let me also add d mu, which is when you have a derivative of some field. Also, this is transformed as a vector. You remember. And let's see. Oops. How all the other discrete symmetry apply to each of these guys. P, T, C. So under parity, this is invariant, so it goes into itself. Right? Gamma naught, 1. This, because you get gamma naught with the gamma phi, you get the minus. So this is minus 1. This guy here, gamma naught, the zero component does not transform, the I component transforms. Okay, how do we write this? Let's write it like this. This notation says that when mu is 0, it doesn't transform. When mu is non-zero, you get a minus 1. I don't want to write all the components, okay? What about this? Well, there is an extra gamma phi, so we give an extra minus time the vector. And what about this? Well, for each gamma mu, when you encounter gamma 0, you get a minus 1 to the mu, so you get minus 1 to the mu, minus 1 to the nu. What about this? When you invert the x in x prime, you change the sign of the space component. It means that when you take the derivative of the space component, you get a flipping sign. So also this will go like -1. The mu of phi will transform as a vector. Okay, so this is our list of parity transformation. Time reversal. Time reversal, you have to trust me, because I'm not going to explain each transformation. So this is invariant. Well, after all, it was the mass term of the Lagrangian which was invariant. Gamma phi, you have gamma 1, gamma 3, they go through. There is anti-unitary, there is a minus from here, you get -1. Vector, we saw it is -1 to the mu. Gamma mu, gamma 5 is -1 to the mu. Gamma mu is -1. Oh, sorry. Here also put an I, because otherwise it would be non-emission, this anti-emission, this is a commutator. -1 nu. You can check all this, since now you have all the formula with the property of transformation of the T, C, blah, blah, for each of them. It's a good exercise to see that you know how to implement, how to deal with all the transformations. And what about d mu? It goes to -1 mu, because only the time component flips and the space component does not. Okay, and then finally charge. Well, psi bar psi is invariant. I psi bar gamma phi psi goes to -1. Sorry, +1. Mistake. The current psi bar gamma mu psi, we argue that it must flip sign, because a charge and the charge conjugation must flip sign. But you can check. Gamma mu gamma phi does not. The tensor does flip. The derivative doesn't even know what the charge conjugation is.
For the T, the third one is...
For T,
Yeah.
the third one is -1 to the mu. Yes, because it's a vector. It's not x. X has this, but it's a vector. So if you imagine momentum. For momentum and the time translation, the special part changes sign.
Okay, yeah.
Okay, now you can combine all of them into C, P, T. Let's compute what happens if you do all three together. This product is +1. This product is +1. This product is this and this is 1. There is a minus. This one is also minus. This one is plus. And this is minus. Notice that all the objects with the odd number of space-time index mu flip sign. All the ones with even number are invariant. So your Lagrangian, if it's Lorentz invariant, transforms as a scalar, it's invariant. This is part of what is called CPT theorem, which states that any consistent Lorentz invariant local quantum field theory is CPT invariant. So CPT is always conserved. Instead, individually, C, P, or T can be violated. And indeed, we know interaction violate P, interaction violate T, or CP, because CPT is not invariant. It's not violated. But CPT will never be violated. If you find experimentally CPT violated, either you have Lorentz breaking of Lorentz invariant, or there is some non-locality in the theory. Any Lagrangian you can construct, which is local and Lorentz invariant, will automatically be CPT invariant.
If we didn't have any internal symmetry for our fields, then we would only have E and T, right?
Yeah, yes, you just say that the field under, for example, a real scalar field, under charge conjugation, it goes into itself. So if you want, you can define, when you say that phi is equal to phi dagger, you just say that the particle is the same as the antiparticle, so the charge conjugation maps the particle into itself. So it's the identity operator, it doesn't do anything.
But we could still apply the parity and time operator just in terms of the space-time
Yes.
sign change. But when we have the internal rhythms, then charge conjugation is completely an internal parity exchange. I don't know if I'm saying this right.
Sorry, say it again.
Charge conjugation is
Yes.
always about internal sign changes between the fields, not about the space-time coordinate sign changes.
Yeah, it doesn't touch on the space-time part.
Parity can be both at both sides, like
Yeah, as we saw for the scalar field, you can mix parity at the end. Parity sometimes is preserved only in a mixture between some internal parity, or in other words, on scalar field, which we didn't write here, parity can have an intrinsic phase, exactly like psi bar gamma phi psi. Psi bar gamma phi psi under parity transform with minus itself. So you can define a scalar phi which is even under parity, where this will be plus, and one which is odd, which is minus. It's both possible.
but all these three CPTs are every possible CPTs that one can apply on the case.
You'll be guaranteed that any Lagrangian you write, which is just Lorentz invariant, so it doesn't have a scalar, and it's local, so it's only products of operators at the same point to define number of derivatives. For those, you'll be guaranteed that you can define a P, a T, and C such that the product is conserved. Then sometimes C acts trivially, sometimes P acts non-trivially on the fields, but you'll be guaranteed that it exists. One combination exists. Of course, here I just did the fermions. The theorem applies to any field. Okay, sorry, I went quite over time.